First problem, you are finding an actual infinite sum. You're only going to be asked to do that if you have a geometric series as far as this test is concerned. So make sure you first of all figure out why it converges. What is the R? The R is easier to find if you look at where is n located. And having the plus 1 in the 2 to the n plus 1 is the same thing as having 2 to the n times 1 more 2, which is really only affecting the first term. So realize that you could rewrite it in this way where you can see that the R is 2/5. But if you don't see it, find the first term, find the second term, and then divide them, and you'll see the R. You have to find the first term anyway. So what is the first term? Double check what your starting n is and make sure that you plug that starting n into the n's and think about it. So plugging in 0, that means I have 2 to the 1 times 3. Plugging in 0, I have 5 to the 0, which is 1. And also I can look at it in this simplified format and perhaps see a little bit better that it is 6 for my first term. So the formula for the sum of a series is the first term over 1 minus r. And a little bit of fractional fun later. And that is going to be 10, if I can arithmetize. There we go. Number 2. The only power series that you are dealing with as a known power series is the geometric power series that always starts off with the function 1 over 1 minus x. You want to plan out what you're doing by first doing those things to this function. Then do those exact same steps to your series. I have to create this integrand before I can integrate. And to create that integrand, I need to see what's different. And that's what's different. I can get this if I substitute a 3x into the x. And then I just want to look at what that actually does. So here I am substituting it in. And then I want to simplify that. Well, anyway, just write it out. See, yes, that's the integrand. Then my next step is to integrate. Now I am integrating 1 over 1 minus 3x. I need to see what I'm actually getting when I go through this integral. So do the u substitution. Think about what that du is. And then I'm going to divide both sides by -3. And now I can see that I will be replacing my dx with -1/3 times du, and I can pull that out of the integral if I like, and then it's 1 over u. I'm not going to need the absolute values around the u because of the interval of convergence, but I do need to put in what the u is. Now, I need to remember exactly what am I supposed to do. All I'm supposed to do is integrate that function. Maybe I'll cut part of this out. Anyway, I just realized that that was a whole bunch of a waste of time because I'm not integrating to get to a function. I'm just integrating. So I substitute in the 3x, and then instead of integrating the function, I'm integrating the power series, and then I will be done. So I'm going to start off with 1 over 1 minus x is equal to, and I'm going to write the first few terms. And also keeping in mind, I only need a third degree power series, and I'm going to integrate, so that's enough. And let's put squiggly equal. Substitute in 3x. And then I'm going to separate the 3 and the x. Otherwise, I've got to go through a u substitution. Don't want to do that. So 3 squared times x squared. Now this polynomial, I can just integrate. So as I integrate, I want to remember that I'm starting with c plus, and then integral of 1, integral of 3x, and then, and that is all you need to do. It is an indefinite integral, so you're done at that point. Now again, using a known power series, that means we're going to start with 1 over 1 minus x. Now, kindly, I see that 1 minus x in the denominator right there. When I see this squared, your life is going to be easiest if you take the derivative to create that denominator squared. So I'm going to differentiate. And I'm going to write d dx of, and I'm going to rewrite it with a negative 1 exponent. And then here comes the derivative. Negative blah to the negative 2. Plug in baby, multiply by derivative of baby. The two negatives make a positive, and I end up with 1 over 1 minus x parentheses squared. And that's getting me to the denominator I wanted to get to. And that was just in one step differentiating the original power series. After I do that, my next step will be multiply by x. And when I do that, my function will become what I was intending it to become. So I've got 2 steps to do. I'm going to start with 1 plus x, and so on. I should probably check what I'm asked for. First 4 non-zero terms and the general term. So I differentiate. When I differentiate, I am going to get derivative of 1 is 0, and then I'm starting really off here with derivative of x is 1, 2x, 3x squared. That's only 3 terms. And then integrating x, or differentiating, and differentiating the general formula. And then multiply by x. So I'm taking the result I just had and multiplying across the board by x. With the formula, if I am taking that formula and I am multiplying by another x, then it's n minus 1 plus 1. The exponent is just n. And that would be my final answer there. For this next one, I'm supposed to create a natural log function. I know that to get there, I'm going to integrate. And I prefer to first make the denominator become 1 plus 2x. And when I say denominator, I mean the denominator of this rational function. It starts off as 1 minus x in the denominator. I can make it 1 plus 2x by substituting in a negative 2x. So then I'm going to demonstrate the substituting in of negative 2x. And then recognizing that that is having in its denominator what I need to have in a logarithm. I've only done one thing so far. The next thing I'm going to do is I'm going to integrate. And I'm going to start by integrating just this function and see what I actually get. I need to do a u substitution. When I divide both sides by 2, I can see that I'm replacing the dx with 1/2 times du, and then I'm left with 1 over u. Integral is 1/2 natural log of u. I don't need absolute values. And then there's a plus c, but the point of integrating right now is to see what function I'm creating when I do the integration. I need to put the u back in, and then I take a little look at what I have. That is not the function I intended to get. What do I need to do to make it the function I intended to get? And that would be multiply by 2. When I do that multiplication by 2, I will get the function that I was intending to get. Now, when I do the integration of the power series, then I'm going to put the plus c, but in order to create this specific function, natural log of 1 plus 2x, I need to find my c that creates that function. So now I'm going to work on the power series. And using a known power series, write a power series in sigma form. So, sigma form. This is sigma from n equals 0 to infinity of x to the n. When I substitute in the negative 2x, I want to simplify before I integrate. And by simplifying, I mean separate that x. I'm going to distribute the exponent over the multiplication. And now I can see that I have a function with variable x. And if I'm going to integrate that function, I'm using the power rule. And that is going to give me, well, let me write the c plus. And then negative 2 to the n is a constant multiple. Using the power rule, I add 1 to the exponent of my variable and divide by that new exponent. Then I've gotten this. I could actually find the unknown plus c at this point, but I'm going to go ahead and go forward and multiply by 2 to get to the function that I wanted to get to, and then solve for the plus c. So if I take that same formula, let me just do copy paste because I so want to. There's my copy. Paste. Oh, now I don't have to rewrite it. Sometimes I like the computer. Okay. I need to multiply by 2. Now, technically, that does change this to 2 times c, which is just another unknown constant. So I'm just going to say that this is some c sub 1 other constant plus sigma that starts at 0. And what I can do is, if I want to simplify it, separate the negative sign from the 2. Then I can bring together where I have the same base. And that means I have negative 1 to the n. I have 2 to the power of n plus 1. And my x is also to the power of n plus 1. And I'm just n plus 1 out here. Then to find c, I want to plug the center in. The center is x, and I can tell that by looking at the fact that this is not x plus a number or minus a number, it's just x. That means the center is 0. So I'm plugging x equals 0 in both sides to figure out what this c needs to be in order for this to represent the function I intended. I plug in 0 on the left side, and on the left side I get the natural log of 1, oh, that's 0, is equal to this unknown constant plus, and then in this series, when I plug 0 into its x, I am just creating a bunch of terms that are all 0. And if you want to double check, you can always look at if I plug in n equals 0, the first term that I get is a positive 1 times 2 times x divided by 1. My next term is going to be negative 4x squared over 1 plus 1 is 2. And the pattern will continue. If I'm plugging 0 into these x's, I am getting 0. So my unknown constant is the natural log of 1, which happens to be 0. Which means that my actual final answer is just this. Yeah, I did not copy it. Try again. Because I don't want to rewrite it. Paste. Dink, dink. And there we go. There is our answer. Okay. So that takes care of all the problems that have to do with knowing the geometric power series. Keep in mind that if you see an exponent over a parentheses in the denominator, you're probably going to take the derivative. If you decide you're going to go the route of squaring 1 over 1 plus x, let me explain what you're going to have to do. Or that was 1 minus x. If I'm squaring, that means I am multiplying a polynomial of infinite degree by another polynomial of infinite degree. Which I could do as long as I do the multiplication boxes in the reverse direction I usually do polynomials. 1 plus x squared. And then maybe I need to go farther, maybe I don't. But this literally is forever. Then 1 x squared, x cubed. Now, one thing that's nice is if you know a certain degree polynomial, you can realize that this upper left box is your constant term. The diagonal underneath it is going to give you your x term. The diagonal under that is going to give you your x squared term. And I'm going to go back. No, I'm going to go to pink. The diagonal under that is your x cubed term. And perhaps you can see the pattern because each time I'm going to have one more item in my diagonal. So I can recognize that the multiplication is equal to 1 plus 2x plus 3x squareds plus 4x cubes. And it continues with that pattern. So that means that if I write x to the n, I am then multiplying it by n plus 1. Or I could have written n times x to the n minus 1. Same thing. Then all I have to do is multiply by x, and I will have the formula that I intended to have. And I end up with the same thing. And this formula can be written as n plus 1, x to the n plus 1, or n times x to the n. The difference in rewriting that is just the difference in stating, is this x, or is this first term coming from n equals 0, or is it coming from n equals 1? If it's coming from n equals 0, then I need to use this formula to create that term. But if it's starting at n equals 1, then this formula will suffice. And if I don't write sigma to state my starting n, I can use either of these two formulas. So it's up to you how you want to manage it. But I've got to say that if that went up to a degree 3 in that denominator, I would certainly want to go with derivative. If you see a logarithm, go with integration. The only known power series we are playing with on this test is the one for 1 over 1 minus x. So that's always your starting ground. Okay, next is dealing with radius of convergence, interval of convergence. So with all of these, you will be fine if you just simply start with ratio test. So limit as n approaches infinity of plug in n plus 1 times the reciprocal and see what cancels. With 3 to the n in the denominator and 3 to the n plus 1 in the numerator, that will leave me with 1 left over in the numerator. I need to look at my factorials. N plus 1 factorial is n plus 1 times the next term down times the next term down until I reach 1. The n factorials will cancel each other out, leaving me with an n plus 1 in the denominator. Then I want to look at the exponent. On my x, I have a 2n plus 2 when I distribute that 2 over. So I have 2 more x's in the numerator than I have in the denominator, so I'm going to have a leftover x squared as those cancel. Let's take a look at what our limit is at that point. In the numerator, I have a 3x squared. In the denominator, I have an n plus 1. X is only representing real numbers. If I have a real number divided by something that's heading to infinity, the fraction will head to 0. 0 is less than 1 always, so that means this converges for all real numbers. Now, the radius of convergence is infinity. The interval of convergence is negative infinity to positive infinity, which means the same thing as all real numbers. For the next one, I can start again with ratio test. Then I cancel what I can cancel, and I see that I have an extra 2x in the numerator than the number I have in the denominator, and that's as far as I can go. The limit will cause the ratio of n plus 1 over n plus 2 to head to 1, and that means that the answer to the limit is, with absolute value bars around it, just that 2x. It will converge if it is less than 1, diverge if it's greater than 1, but equal to 1, the test is inconclusive, and thus I have to test my endpoints. With this inequality, if I divide both sides by 2, I can see that my radius of convergence is 1/2. Then, if I rewrite that inequality between the positive and the negative, I can see what my endpoints are that need to be checked. I need to check x equals negative 1/2, and I need to check x equals positive 1/2 by plugging them into the x in the sigma. So in that parentheses, I am multiplying 2 times negative 1/2. That will leave me with a negative 1 in those parentheses. Over here, I'm multiplying 2 times positive 1/2. That will leave me with a 1 to the power of n. 1 to the power of n is just going to be 1, so I'm going to erase that exponent. This is an alternating series. It will converge through the alternating series test. This is, you can compare it to harmonic. It is okay for you to say that it is a diverging harmonic series. That makes the interval of convergence inclusive of the negative 1/2 to 1/2, but not including the 1/2. All right, next, number 7. Again, start with the ratio test. Limit as n approaches infinity of plug in an n plus 1. Divided by plug in an n, and since I didn't have a fraction, I'm just going to do regular division instead of times reciprocal. Now, let's figure out what cancels and what doesn't cancel. The n plus 1 factorial is n plus 1 times, subtract 1, n, and then Keep going. I will get a cancellation with those n factorials. I have one extra x plus 2 in the numerator than I have in the denominator. So now what I have is, this is the limit as n approaches infinity of n plus 1 over, nope, not over. We don't have a fraction. This is n plus 1 multiplied by x plus 2. If x represents a real number and n is heading to infinity, infinity times any non-zero real number is infinity. But I did say non-zero. 0 times infinity is indeterminate. However, we know that we always get converge at the center because that will mean that my polynomial is just the constant term and everything else becomes adding 0 forever. So what this means is I'm greater than 1. Infinity is a bit greater than 1. The ratio test is saying diverge for everything except -2. But the ratio test does not tell me whether it converges or diverges at x equals -2. That's an issue of the center always converges. So that means my radius of convergence is 0. My interval of convergence is just a single number. So I'm going to write that as the set of all numbers -2. Now the 8th one, you can keep on going with the ratio test. This one, you have an option of using a geometric series test if you notice it. So what you want to see is, where are your n's located? Your n's are only located in exponents, and that's it. That means you are dealing with a geometric series. If you look at all the previous formulas, n exists right there, that's not an exponent. Keep going back up. N exists here, that's an exponent, but there, not an exponent. Ooh, look, n's in exponents, not an exponent. So none of those are geometric because n has to be only in an exponent to be geometric. So that means I need to figure out what r is. And if I rewrite it as x minus 3 to the n over 5 to the n times 1 more 5, I might be able to see a little bit more clearly that my r is x minus 3 divided by 5. And if I'm aware that that's my r, then I can use geometric series test to know that it will converge if its absolute value is less than 1. I also know that I will get diverge if it's greater or equal to 1. And that's the joy, is you don't have to test endpoints. So multiplying both sides by 5, I can see that my radius of convergence is 5. From there, the center of my polynomial is 3, because that's what makes x minus 3 equal to 0, with a radius of 5 units. So plus 5, minus 5. And I know the endpoints will diverge because I used geometric series test. So interval of convergence along with the radius of convergence. Okay, I'm not putting number 9 on the test tomorrow, so I'm just going to move on and focus on some of these. So let's start with number 10. If you are expected to use the Lagrange error, then what I do is I think about, first of all, what are my nabs? I need to nab certain numbers. N is the degree of the polynomial being used to approximate. That's a 5. A is the center of my polynomial, which it has to say somewhere in there what the center is. And B is the number that I'm plugging into the polynomial to approximate F at that same number. So my B is 3/2. Now, from there, I like to think about the Taylor formula itself. Normally, the Taylor formula is nth derivative at the center. I'm just going to leave some parentheses here. Over n factorial times x minus a to the n power. But because of this being an error, I'm going to 1-up the n's. So I see a 5, I'm going to throw in a 6. And I don't get to find the derivative at the center. I need to look at the largest it can be while its input is somewhere between the A and the B. So I am wanting to find the maximum while this is between 1 and 3/2. Now let's continue though with all that I have to do with that nab part is I need to figure out some maximum number, and then it's over because n is 5, 6 factorial, and to the power of 6. Then the B number that I'm plugging into x minus the center, we can see it right there from our normal formula that we use for Taylor. And then all I have left is this. What is the maximum of the 6th derivative where z is, again, between the center and the number I'm approximating at. So along the x-axis, I see there's 0, there's 1, too far, there's 2, back up, 1.5. So this is the x interval. I am looking at the y values while the graph is in that x interval. Now, I can see that the y values are definitely under 10. And if that 10 works to suffice this inequality, 10 is going to be a much easier number to use. Do realize that if you really zoom in and look at it, you can take a guesstimate of about what number that is, but you have to make sure that you are absolutely 100% positive that it is at or larger than whatever that y value is. You're safest to go with the extremely obvious, it's not going past 10. And 10 is a nice number to use. AP test typically likes to do this. So I can now say that I'm going to replace that m with a 10. 3/2 minus 1 and to the power of 6. And then all you have to do is explain that this is less than 1 over 4,000. And it's good form to say that this is greater than the actual error of the function minus the polynomial. and just basically rewrite what it said, and you are done. You can double check that that inequality holds if you want, or you can move forward. Now, for this one, I'm going to add into the test a statement of use the alternating series error bound to show that this inequality holds. Now, you don't need to do what I'm about to do. I just want to make sure that I'm clearly pointing out to you that P3 of 1/5 gives me an alternating series. I can see that it is alternating series when I look at the formula. Now, if I am approximating the polynomial at 1/5, but I'm approximating it in very specifically my degree 3 polynomial, I need to know what is the first omitted term, provided that this polynomial is an alternating series. The terms, the absolute value of the terms, decrease to 0. And that means that my error is no more than the first omitted term. And the first omitted term is what was going to come next. If you look at the pattern, you can see it was going to be plus something to the third power over, look at those denominators, look at the pattern, 5 squared. You can double check that that is the correct pattern if you go and look at the formula that we are using. And wow, that was silly of me. Yeah, double check. That was going to be what my next term would be. And again, double check. I'm plugging in n equals 4 to get that fourth term. I should have x to the fourth, positive 1, and then 4 plus 1 is 5 being squared. Yes, that is my next term that is first not written. So therefore, I can say that my actual error of estimating f of 1/5 through this third degree polynomial is less than the absolute value of this, but since I don't have a negative, I'm not going to bother writing absolute value. That's 4. And that is less than 1 over 15,000. You can double check that that inequality holds, but that's enough said. Okay, finally, absolutely converge, conditionally converge, and diverge. You want to remember that if something actually does come out as absolutely converge, the only thing you need to do is take the absolute value of the formula, look at the full series that uses the absolute value. If that converges, then you are absolutely convergent. This is all you need. That means one infinite series to determine. If you are conditionally converging, you have to go through two entirely different determinations of two sigmas. you're going to have to figure out what's going on without the absolute values and what is going on for these series with the absolute values. If it's conditionally convergent, then with the absolute values, it's going to diverge. Without the absolute values, it is able to converge. And both of them have to be done to express conditional convergence. For divergence, don't go straight to the absolute value. If you're dealing with diverge, then that means that even if you let the negatives and positives play together, you're still getting diverge. So you want to first decide which of these three you think it is so that you know, should I start with this series or should I start with this series? So that you don't end up wasting time. As I analyze this for number 12, I realize that when I absolute value the formula, I am getting a P series where the P is 1/3. That's going to diverge, but I've got an alternating series. As an alternating series, it will converge. So that means I have to do two different tests. So I've got an issue. I've got two issues going on, and it's important to distinguish the difference. There is, I am using alternating series test. And actually, I'm going to lasso and move this so that I can say specifically, if I am testing this series with the alternating series test, I need to state first, it's an alternating series. The absolute value of the terms decrease to 0. Then I'm allowed to play with just the formula itself. I think I'm going to lasso it back over here. This isn't looking at the series of the absolute value. This is looking at just the absolute value. The absolute value I just realized I said too much with number 12, and I'm about out of time, so I'm going to have to come back to this later.